So, where's my blue bar? Yes, the blue bar is there. We are recording. Now that's a good thing. And the next thing is share screen. Let's see. I'm really paranoid now. I'm totally paranoid now. And can you see my screen? Yes! These are 3 yeses. Life is good. Oh, that's at least so far it works. And and there's a big yes von war. And no, that's great. That's great. I mean, that's fantastic. This is what I wanted to say. Yes. As I said, the situation yesterday was less than great, and even worse, Virgin Media completely cut off the sort of the area where we live near Dover. So I didn't even get any emails or anything. And well, actually, interesting you say that, Hussein, because today is BI308. So yesterday was BI301. And luckily, in my infinite wisdom, I always had factored in a contingency session in my schedule, in the plan for what I'm going to do in a module. Yeah, and therefore it's not such a big problem that we missed out on the BI301 session yesterday. So all is not lost, and we will cover all the topics that I wanted to cover, that we need. However, for the BI301 people, just, for the BI301 people only, I know we are in the wrong module, but I think I already sent out the link for people, because I have set up sort of metabolism problem questions. And here are some, and you should have the link to this. So here you get, you can practice things with model answers. You get questions, give me another card, and things like that. But I will send that out again in an email or in an announcement on Moodle. So you're not missing out, and you can do some practice questions for the program level multiple choice quiz next week, and then for the exams. So all should be good. Now let me go back to the BI308 because we want to cover a little bit of stuff in this module today. And Bernardo has already posted the link, so that's great. And I just can say hello, everybody. Lovely to see you. Thank you very much, Bernardo. Young, faithful, fantastic. A big round of virtual applause for Bernardo. So let's hope that today is a better day. And I'm feeling very positive. Thank you very much, Charlotte. I hope everybody else is positive, and hopefully things will be back to normal. I mean, yesterday, for the new assignment, do we need to get 100% to be able to submit? Absolutely. And for those of you who have looked, this is basically pretty much the same assignment that you have done before Christmas in week 12, I think. And the reason why I've set you almost the same assessment again is because I want you to practice these calculations. Now, people have asked me when the second assessment is due, and it is all on the website for which I've sent you the link. I would have liked to set the deadline much closer to your exams, because then you can use that as a sort of a revision tool. However, our lovely people from the admin office told me that I am not allowed to mess around with deadlines and due dates. So they basically forced me to put the deadline that is on the website, and that is also on the student data system. They forced me to stick to that deadline. I'm terribly sorry. But what I will do is I will keep the quizzes open so that you can still use them for practice purposes. But for this second assessment, it's just simply taken from the practice calculation website. And I think with that, you have a really good resource there. And yes, you do get a week extension as far as I understand. So I hope this makes sense. By the way, you have received your exam timetable. So you know when your exams are? Excellent, good. Oh, you've got Saturday exams. Oh, lucky you. Mind you, you are quite lucky. You got the timetable. I didn't. So I only found out through you guys. Anyway, let's get started. And very warm welcome to everybody. Very good afternoon now. And what I want to do with you today is I want to expand a little bit on the t-tests that I introduced last week. And remember, last week I showed you how we can do a two-sample t-test. Two-sample t-test. I told you a little bit about the story behind the t-tests. And how this was developed. I told you about the story of Sir William Gossett, and that he has been credited with being the inventor of this student t-test. Although technically, if you dig a little bit in the histories of mathematics, it's not entirely true, because this t-test and the theory has been developed previously. But Gossett was just aware of what has been done and developed it further and actually applied it to real life example. So he was basically standing on the shoulders of giants, but put everything together, and I think that is absolutely amazing. The basic concept of this two-sample t-test is that we compare two samples, so sample 1 and sample 2. We compare these samples. We know that the means for both samples are not the same, because this is due to sampling error. But what we do is we just simply say we take these samples, we try to figure out what the population mean is. So what the population mean is from which we took the sample. And then we just simply say, are these two population means the same? And that is basically our null hypothesis. And that is the principle of this two-sample t-test. We basically said what we do is we take the differences between these two samples, and we would get a new distribution, a difference distribution, which probably looks a little bit like that. So x bar minus x bar 2, which, because we try to figure out what the difference in the population would be the same as the population, the difference in the population means. And then we basically try to figure out whether 0 is actually within this distribution, or we try to figure out what would be the probability of getting a difference of 0. So that is basically what this two-sample t-test is asking. What is the probability? What is the probability? Probability that the difference between the means, is 0. And if the probability, if this p-value, if p is lower, say, than 5%, if the probability that we get 0 for the difference, if the probability is lower than 5%, then we would usually say they come from samples, they come from different populations. Different populations. So we would reject the null hypothesis. If the p-value is larger than 5%, that's our alpha significance level, then we can't really say that they come from different populations. We say they are probably from the same distribution or same population. And I write it very carefully. They probably come from the same population. Okay. If P is low, H naught must go. They don't come from the same population. If P is high, higher than 5%, if P is high, H naught can stay. Okay, so I also showed you how you can actually do this two-sample t-test in this Evan Miller calculator. When can you actually, when should you use a two-sample t-test? This is actually a really important question, and a lot of our final year students are currently falling over about this. So a two-sample t-test should be used, yes, when you have two samples. If you have more than two samples that you want to compare, more than two samples, T-test is not the right test to use. In this case, you would use a different test, which is called Anova, which stands for Analysis of Variance. This is when you have more than 2 samples. You should use a t-test if you have continuous data, if you've got count data, like frequencies, or if you have proportions, then you should not use a t-test. You should use either a Poisson or this binomial test, right? So continuous data, 2 samples. Also, you should use it if the population standard deviations, and I write it like that, are unknown. Because we replace these population standard deviations with estimates from our samples, with the standard deviation of sample 1 and the sample standard deviation from sample 2. So we don't know the population standard deviations, we estimate them with S1 and S2. And if this is the case, we should use a t-test. If we have sigma 1 and sigma 2, the population standard deviations, then we would not need to use a t-test. We could just simply use the normal distribution for that. Another criterion for that is that our samples come from normal distributed populations. So we assume that the populations here, these populations, that they show a normal distribution of the data. And that is also a sort of a prerequisite for a t-test. Usually we don't know whether this is actually true, but it's usually not such a, a bad assumption, because most of the times we will actually deal with populations that have this normal distribution. If, however, it turns out you don't have a normally distributed population, and the question is, how would you know? Well, there are some tests for that. But if you don't have such a normal distributed population, usually you get away with just using a t-test. It's not terribly accurate then, but it points in the right direction. Only if your populations are totally out of whack and have nothing to do with a normal distribution, if they are totally weird or something like that, then you run into a problem and you can't use a t-test. And the last criterion that people very often use is that if the sample sizes are smaller than they usually say 30. And that is one thing that I don't really like, because they say, oh, a lot of people say, oh, my sample size is larger than 30, so actually I don't want to use a t-test, I just use a normal distribution. And that is not right. So if I think this is sort of, should be in brackets. I would not use this as a criterion for a t-test, but I think these 4 criteria should be met. And the reason why people say 30 is sort of the cutoff point, it is because the t-distribution for a sample size of 30 start to look pretty similar to a normal distribution. And in a normal distribution, we don't really care about the size. But I think these 4 criteria, 2 samples, continuous data, we don't know the population, standard deviations, and the normal distribution, these are, I think, important point. And it's just simply, even with larger sample sizes, there are differences. And if you can use a t-test, why not use it? Why would you revert to a normal distribution just because of, is it easier? Well, not really, because what I'm going to show you today is how you can actually use the t-test in not just with the online calculator. The online calculator gives you a lot of information about the distributions, but very often we are not really interested in these information. For the for your practical, for the assessed practical, for the data analysis, you would use the online calculator. But very often we just want to know, quick and dirty, is there a difference between the samples or not? So let me show you today how you do that in Excel. So here, can you see the screen in Excel?
Yeah.
Excellent. So here we have an example. We have 2 samples. One thing that you probably note is the sample sizes N1 and N2, they are not the same. And we don't need that for a t-test. Although, here comes a disclaimer. The t-test that you have discussed, or that some of you have learned at school, the standard t-test, the common t-test that you have learned, really requires that the 2 sample sizes are the same, and also that the variances are pretty similar. They don't have to be exactly the same, but they should be very similar. Then you have been taught to use the common t-test. But in our case here, we very clearly see that the sample sizes are not the same. And therefore, what we will use is a modified t-test, which I told you is called the Welsh Test. It's also a t-test, but it has a little bit more flexibility in it. The Welsh t-test does not assume that the sample sizes are the same, and it does not require the standard deviations to be the same. And most programs will actually calculate a p-value based on Welsh Test. Why people still get taught about the common or the normal t-test, I don't know. They are not exactly the same, because And there is a slight difference in how you calculate things between these two tests. But since we don't usually calculate them by hand, we are not too worried about the differences. Just let me tell you that always go for what is known as the Welsh test, because with the Welsh test, you don't have to have the same sample sizes and you don't have to have the same standard deviations. Always, my advice would be always do a Welsh test. The Evan Miller calculator uses the Welsh test, so you don't have to worry about it. And I show you how you actually do that in Excel. Okay, are you ready? Let's try to figure out if there is a significant difference between these two samples, between sample 1 and sample 2. Okay? And how would we do that in Excel? It's really easy. So what we need to do is we just put in an equation equals t dot test, and it comes up with it. And it asks us for the first array. That's our first sample here. So that's the first sample. It asks us for the second sample, sample 2. Okay, now it asks us for tails. And for tails, we are always going for a two-tailed test. Two-tailed means we a two-tailed test means that in our alternative hypothesis, we just simply say the population means are not the same. So here, always put in the number 2, right? And we have got 1 point left, and that is the type of the test that we want to do. And for the Welsh test, if we have 2 samples in the Welsh test, in Excel, this is indicated by the number 3. So we have our 2 samples. We have the number 2 for a two-tailed test. And we have the number 3, which indicates the Welsh test. And that is our p-value here. So let me write this out again. We have t-test, sample 1, sample 2. We have the number 2, which is two-tailed. And we have the number 3, which indicates the Welsh test. Okay, so we get a p-value of 0.1103. What is the verdict? Do the samples come from 2 different distributions? Is there a statistically significant difference between the samples? If we say alpha equals 5%, are the samples different? Are the samples different? Remember, if P is low, H0 must go. So P smaller than 5% means we reject the null hypothesis and we say mu1 is not the same as mu2. If P is larger than 5%, we say they can come from the same population, the samples, and there is no difference. So in this case, the p-value is 0.1. So 0.103 is certainly larger than 0.05. So P is larger than alpha. P is high, so H0 can stay. Two samples probably come from the same, population, or we can say there is no difference. No statistically significant difference. Significant difference. So if we, for example, had sample 1 was with a drug, sample 2 was without a drug, we would say the drug doesn't really make any difference. What we see here is just simply sampling error. Okay, does that make sense? So that is how you would do a two-sample t-test in Excel. Now, I told you that we are doing different t-tests today. So what do I mean by that? Well, here is another t-test that I want to show you. And we have just one sample. Sample 1, let's say metabolite. Again, we measure metabolite. And we want to compare this one sample with a known reference value. So here we don't have two samples that we want to compare. We have just one sample. How are we going to do that? We want to know whether, for example, the reference value that we know, let's say we have a reference value of 19, and we want to compare that and okay. So how do we deal with that? Obviously, this is no longer a two-sample t-test, is it? Because we've got only one sample here. So this would be, what would you call that? Obviously, this would be a one-sample t-test. We have a one-sample t-test. How are we going to deal with that? Interesting question, isn't it? Well, actually, What we are looking for is really, we are basically taking a t-distribution, that's our sample here, t-distribution for our sample, and we want to know what the probability is that we get a value of the reference The reference number is something that, for example, people have measured before or that has been published in the literature. So, for example, we say we measure the concentration of a metabolite in in 4 volunteers, and we know that a healthy person has the value of, let's say, 19. For this metabolite, 19 millimolar or something like that. So we want to know, is there a difference between the sample and the reference value? Or what is the probability that there is no difference between our sample and the reference value? And the way you can very easily do that is you do a sort of a trick. You add the reference value again, right? What you then do is you say, right, this is now a 2-sample t-test where I just entered the reference value twice. So I can now just simply do an ordinary t-test. T-test. Sample 1. Array 2. That's this one here. I do 2 tails. As we discussed, and I use the Welsh test for this one here. And I get my p-value. Look at that. I got a p-value. So here is my p-value. Why is that not working? So this would be my p-value here. So I get a p-value of 0.0025. What does that mean? P is higher or lower than 5%? Yep, P is lower than 5%. So that means statistically significant difference, significant difference between the sample and the reference value. So if this reference value indicated a healthy person, then the sample very clearly is different from the reference value. Does that make sense? This is known as a 1-sample t-test. where we compare just one sample with a reference value. The way we deal with that is we enter the reference value twice, so that we can again do really a true sample. It's sort of a dirty trick, if you like, that we have a second sample, but in this case with exactly the same identical numbers, but we still can do a Welsh test, a two-sample Welsh test with these reference values. So this is a one-sample t-test when we want to compare just one sample with a reference number. Does that make sense? Right. Now, there is one more t-test that I want to show you. And this t-test actually uses two samples again. Yeah, hey, great. We've got two samples again. So we are back to a two-sample test. Two-sample test. T-test. But there is a twist to it. In our previous example, these two samples were totally independent from each other. Independent. There was no association between the two samples. I took some volunteers and took the blood and got sample 1, and I got another set of volunteers and got another set of measurements. So this is a two-sample independent t-test that I showed you here. Now, in this case here, the samples are actually paired. Samples are no longer independent. The samples are not independent because what I have done is I have 6 patients here and I test the metabolite concentration before I do an intervention, and I measure a value here, and then I measure the same metabolite after I have done the intervention here. Do you see what I mean? So here we have a pair of samples, which is before something happens and after it happens. But they are connected to each other. These two samples that we have, sample 1 and sample 2, they are in a way pairwise connected with each other. Do you see what I mean with that? What do you think is a sort of requirement for that? Would our two sample sizes, do they have to be the same in this case or not? N1 and N2. Do they have to be the same? Absolutely, they have to be the same. N1 equals N2 because they are connected. They are pairwise. So that's really important that we bear that in mind. Whereas if we looked at this case, you see, N1 and N2 are not the same. They don't have to be the same. They can be the same, but it's not mandatory that they are the same. Whereas in this case, the two-sample t-test, where the samples are dependent, or you also see that as written as paired. You find this as a paired t-test because the two samples are connected with each other, right? Does that make sense? So, how are we going to find out whether there is a difference? So our question is there a difference between concentration before and after the treatment? And this is actually a very common scenario where we say, is, for example, a drug efficient? And what we do is we can either just simply hand out trials of the drug and have this scenario where we have random people where the samples are independent, or what we can do is we just simply do a patient trial where we have here a certain number of patients. We check within sort of the same patient whether the drug had a difference. So how are we going to test this? And this is where the Evan Miller calculator actually can't do it. It doesn't have the opportunity to do this paired t-test. But in Excel, it is actually quite simple. So we start again with equals t-test t-test. Let me move that. It again asks us for our first array, that's the sample for this one here. No, why is it not doing that? Probably, I think what I need to do is probably need to remove my scribbles. No, doesn't do that. Okay, let's try that again. I apologize. Okay, that would be C5 to, where are we? C10. C10. So that's our first sample. We do the array 2. That's in cells D5 to D10. Okay. Tails. Again, we do a two-tailed test. Always do a two-tailed test unless you have a very good reason not to. We do 2. So far, so good. Remember, we did the Welsh test with a 3 that indicated Welsh test, independent samples. In the case of a two-sample paired t-test, the type is 1. And let's press enter. So what we've got here is our p-value. This Excel, it drives me insane. Well, let's type it down here. P value. So here we've got our p-value of 0.039. What does that mean? P, is that smaller or larger than alpha? If we say alpha equals 5%. Yep, we reject, it is smaller than alpha, and we reject our null hypothesis. And therefore, we say, yes, there is a significant difference in the samples before and after the drug. After admission of the drug. So therefore, our conclusion would be, yes, the drug is actually doing something. So there is, very clearly, there is something going on. And if you think about it, so this is this two-sample paired t-test. What does this test actually look at? What we are looking at here is we compare these two samples with each other, but because they are paired, what goes on behind the scene is that the program actually calculates the difference between each number before and after. It calculates the difference. Let's calculate the difference. Equals no, let's not calculate the difference. Just take my word for it. What the program does is it calculates the difference between the different. So let me write this down. Let's go over to here. That's easier. So before and after working with Excel and a pen is absolutely a pain. Patient 1, 2, 3, 4, 5, 6. The program calculates the difference between these numbers. So it calculates the difference between this one, this one, this one, this one, this one, this one. So we've got new samples, a new sample here, the sample difference. And what it does is it does the t-distribution, but now with the difference. And it asks, is the difference, what is the probability that the difference is actually 0? And it is familiar because that is exactly what we have done before, where we just simply say we have just one sample. So this is the same as one sample t-test with a reference value of 0. So we just simply take the difference, we treat that as a new sample, we just have one sample here, but we compare that to 0, this reference value. So what we could do, if we wanted to, we could do exactly the same here. So if this was the difference, our sample, so you probably don't see that. This would be our difference here. It's not working, but hey, and we would compare it to a reference value of 0. So what I have shown you today is how to calculate in Excel 2 sample independent t-test. That's equals t-test sample 1, sample 2, 2, and 3. I showed you how we can do one sample where we compare to reference value. And we actually can use the same equation, but we just simply put in the reference value twice. And we use a 2 sample dependent t-test when we compare before and after a treatment. And here we want to know, is there a difference? Or are they the same? If they are the same, the difference is 0. If the difference is not 0, they are not the same, right? So here we would use t-test sample 1, sample 2, number 2 for two-tailed, and we would use 1 that indicates it's a paired test. Number 3 indicates it is a Welsh test independent or unpaired. I hope this makes sense. And you now should be able to do lots and lots of t-tests if you so wish. But remember, if you have more than 2 samples to compare with, you cannot use a t-test. You have to use a different test, which again is called Anova. This would be, where did I put that? Have I put that here? And this would be usually what is called a one-way Anova. And in a one-way ANOVA, you would compare mu1 equals mu2 equals mu3 equals mu4, and so on and so forth. So I hope this makes sense. I will upload these notes. I'm not entirely sure what I'm going to do with the Excel, but this is not easy to upload Excel. But these notes here, they will definitely go up on the class materials. Thank you very much for tuning in, and I hope you have a wonderful Easter break. Relax, enjoy. Hopefully the weather is not too grim, and eat lots and lots of chocolate, because it is very well known that the well-being of people is definitely dependent on the consumption of chocolate. So you can do this exercise. You just simply check out what is your mood before you eat chocolate, and then check out what happens with your mood after you've eaten chocolate. Do this score and see whether it's statistically significant. Happy Easter if you celebrate. Take care. Have a good weekend. I see you next week. Bye-bye.